2.6 Logarithmic Functions. How do you find the particular equation of logarithmic functions algebraically? So just a reminder about logarithmic functions and their graphs. If you remember, if I'm given an exponential function, the logarithmic function is the inverse or the reflection over that line y equals x. So here we have the exponential function y equals e to the x power. So you can see that one of the points on that graph is 0, 1. Right? If I plug 0 in, I get 1. Okay, reflecting that over then gives us the point 1, 0, which is on most logarithmic graphs if they haven't been shifted horizontally or vertically. Another important trait is that the y-axis is a vertical asymptote. Okay, and the same is true with the base 10. Okay, or any base really. So most of your exponential functions, if they haven't been transformed too much, are going to look like this. They're going to go through 0, 1, and the logarithm with that same base is going to be a reflection over that line y equals x, which basically means that they're inverses of each other. And as a reminder, we have these in our parent graphs as well. So starting with, y equals log base b of x, there's no shifts, there's no dilations, okay? But if you wanted to put all those transformations in, you'd have a times the log base b of x minus h plus k. And when the base is some number greater than 0, you're going to end up with an increasing graph. And when the base is a fraction, you're going to end up with that decreasing graph. And again, that y-axis is your asymptote. That asymptote shifts horizontally. For example, if h was 3, then my asymptote would move from being at y on the y-axis to where x equals 3. So I'd move it 3 over. And then this point, 1, 0, would become 4, 0. Okay, just a quick reminder. So here's something new that maybe you didn't know. Logarithmic functions have the multiply-add pattern. So for every input, I'm going to multiply by a constant to get the next input, and the outputs increase by a constant. Okay, so this is increasing by 1 each time. So putting that into practice, let's move on to example 1. A, show that the values in the table have the multiply-add property, which then we can conclude that this is a logarithmic function. So going from 1 to 10, 10 to 100, 100 to 1,000, I notice each one of these is multiplied by 10. So there is a multiplication happening of 10 to get to the next input on each of these. Well, what's happening on those outputs? It looks to me like they're increasing by 1 each time. So that's how you could show that they have the multiplication or the multiply-add property. All right, for B, we're going to use the first and the last points to find algebraically the particular equation of the natural logarithmic function that fits the points. So for this particular function, I'm going to keep that stretch factor, that a, that dilation factor, and then I'm going to do log base b of x plus k. And actually, for base b, I think it would be better if we just left that. Maybe it would be better, actually, if we just use ln. Let's just use the natural logarithm. That's the one that appears most often, so we might as well go ahead and use that one. Okay, so first and last points. So my first point is 1, 2. Last point is 1,005. So I'm going to come up with two equations using this general form, and then use substitution to figure out what a and k are. So first equation could be 2 equals a ln of 1 plus k. And the second equation will then be 5 equals a ln of 1,000 plus k. And probably the best way to do the substitution, what I'm seeing is the easiest, is that the k's, if I, for example, negated this entire second equation, the k's would cancel out. So that's what I'll do. I'll multiply this whole equation by a -1. So let's see, rewriting this, I'm going to have 2 equals a ln of 1 plus k. Hopefully you're thinking to yourself, oh, I know what ln of 1 is, because we just went over that on this graph, right? The ln of 1 is going to be 0. That might make our life a little easy in the future there. Down here, I'm going to distribute that negative 1. So now I can see that those k's reduce when I combine them. Let's see, I'm going to end up with negative 3 equals a ln of 1 minus a ln of 1,000. Hopefully you're thinking to yourself, I see a common factor here. A and A, that's a common factor, so I could distribute or reverse distribute that or factor that out. And then maybe you're thinking to yourself, there's subtraction. These are logarithms with the same base, so I could use that quotient property. And then from there, to get A by itself, I'll divide both sides by this ln of 1 over 1,000. Which, when you put that into your calculator, you get approximately 0.434. Okay, now taking that value, and I think to be exact, I'm going to take this value like before I actually put it into my calculator, and then I'll go ahead and I'll solve for k. So I'm going to plug it. Why don't I plug it back into the first one here? I'm going to take this, plug it back into this first equation. So I get 2 equals, well, instead of a, I'm going to put negative 3 divided by the ln of 1 over 1,000 times the ln of 1 plus k. Now, what did we say the ln of 1 was? Well, the ln of 1, again, going back to that graph, is 0. So this whole piece right here just becomes 0. So we end up with 2 equals k. So taking my a and my k and plugging it back into my general equation, I'm going to say it's approximately, which again, if I put this into a calculator and I'm going to not get these exact outputs. It would be better maybe to use this value. But what I've noticed your textbook doing for the answers is they're rounding. So you're not going to get the exact same values, but you're going to get pretty darn close. And so in C, they want us to verify that the equation in part B gives the other points in the table. So you could plug in any of those points that you wanted to. Let's see, let's get my calculator out. So where's my equation? So why don't I plug in, how about I plug in 100? Oops, you gotta do ln of 100. And like I said, it's really close. It's not exact. If I wanted an exact answer, then I would leave A as negative 3 over ln of 1 over 1,000. All right, moving on. To example 2, the earthquake problem. So you can gauge the amount of energy released by an earthquake by its Richter magnitude, which was a scale devised by seismologist Charles F. Richter in 1935. The Richter magnitude is a base 10 logarithmic function of the energy released by the earthquake. These data show the Richter magnitude m, so Richter magnitude is our m, for earthquakes that release energy equivalent to the explosion of X tons of TNT. All right, so X is going to be the tons of TNT. Looks like a lot of tons there. And then M is going to be our Richter magnitude. We're pretty familiar with earthquakes here, so this should kind of hit home as we go through this. Be thinking about the different earthquakes that we've had here and what their magnitudes are and how those felt. Okay? All right, so A is to find the particular equation of the common logarithmic function m equals a plus b log x that fits the two data points. So they're using some different variables than what I've used. Now, m and x come from the inputs and the outputs, but a, I actually use that as k to kind of just remind you that that's that vertical translation. And b is our stretch factor or our horizontal, or sorry, our dilation. Okay, so I am going to instead write a log x plus k. So using the same standard equation that we used before, okay, and using some variables that you're familiar with. Okay, so we're going to do pretty much like we just did. So for a, I'm going to use m equals a log x plus k. Plugging in my two data points here, so I've got the magnitude m is 4 equals a log of 1,000 plus k, and then my other equation will be 6 equals a log of 1,000,000 plus k. So right away I can get rid of those k's by basically negating the second one, or really subtracting the two. But I'm going to go ahead and rewrite them because there's a lot of room for error here if you're not really careful with your math. So distributing this negative is very important. Now combining them, I get negative 2 equals a log of 1,000 minus a log of 1,000,000. And you might see a shortcut here. Maybe from the last one, you could have said, well, I knew I'm going to have to factor out that a anyways, and then I'm going to be left with the quotient property. But I'm going to go ahead and do this in a couple steps so that I don't make any errors. All right, so I'm going to factor out that a. Then I can see that I'm going to use the quotient property. Then I'm going to simplify so I can see that I can reduce by 1,000. And then I'm going to solve for a. Okay, so that's my value for a. Now this actually ends up, if you put it into your calculator, it gives you 0.66666 repeating, which is 2/3. Okay, now I'm going to use that, and I'm going to plug it into one of my equations, and I'm going to figure out what k is. So how about if I plug it in? I like to use the smaller number, so I'll plug it into the first one. So I'm going to take this and plug it into my first equation there. And then solving for k, we end up with 4 equals, well, 2/3. Now, log of 1,000, think about that. That's 10 to what power will give you 1,000? Well, that's just 3, right? So this is really 2/3 times 3/1 plus k. So really, I'm left with 4 equals 2 plus k, or k equals 2. So my final equation, plugging back in my a and my k, is going to be m, oops, let me get on the screen, 2/3 log of x plus 2. Now we're going to use this in b, okay? So use the equation to predict the Richter magnitude for, and we got a few different earthquakes happening here, and one of them I think was just a blasting of TNT. So let's see, the 1964 Alaska earthquake, one of the strongest on record, which released the energy of 5 billion tons of TNT. Okay, so is that, let's see, is that going to be an input or an output? Tons of TNT is my input, so I'm going to input X being 5 billion. So having your graphing calculator, or any calculator at this point, would be helpful. Actually, maybe I'll put this into y equals and then I can use my table. I think I want to start at 5. Okay, so what I'm getting here is 5. This really means 5 times 10 to the 9, okay, which basically, if I was going to turn this into a decimal with 5, like as 5.0, I would have had to move my decimal back 9 places, okay? So that's why this is 5 times 10 to the 9th. And I'm going to move my cursor over so that I can actually see what my whole value is. So I see that it's 8.46598, or approximately, I guess we could just go ahead and round. Usually when you hear about earthquakes on the news, it's usually to the 10th place, right? So it's approximately 8.5 is your magnitude. Now, thinking about the earthquakes that we've experienced, is this a pretty strong earthquake? It is. So I just looked it up, and the strongest magnitude earthquake also happened in the 60s. I think it was 1960, and it happened in Chile, and it was a 9.5 magnitude earthquake. So that was a really strong one. All right, next. An earthquake that would release the amount of solar energy Earth receives every day. 160 trillion tons of TNT. Okay, that seems like a lot. All right, let's see. So 160 trillion is going to be my input. And I believe that's trillion. That's million, billion, trillion. So putting that into my calculator. Oh my goodness, that's huge. So approximately 11.5. That's huge. So that's one that's off the charts. Okay. All right, blasting done at a construction site that releases the energy of about 30 pounds of TNT. So we're going to have to do a little bit of unit analysis here. I know that 1 ton is equal to 2,000 pounds. And if you don't know that, you can always look that up. So let's see, I've got 30 pounds of TNT. So 30 pounds, I'm going to have to do a little bit of unit analysis here. So I'm going to multiply by 2,000 pounds will go in the denominator so that the pounds reduce per 1 ton. All right, I'm also going to divide by 10. So I basically get 3 over 200 tons. So 3/200ths of a ton. Okay, so putting that into my calculator. So let's see here. Let me actually write that. About a 0.8. Magnitude. Okay, let's move on to C. The earthquake that caused a tsunami in the Indian Ocean in 2004 had Richter magnitude of about 9. How many tons of TNT would it take to produce a shock of this magnitude? Okay, so now I'm given my M, my output, and I need to figure out what my input is, the tons of TNT, or the energy, okay? So let's see here. How many tons of TNT? So I'm going to go ahead and just plug 9 in. You know, there's a couple ways you could do this. You could do this on your calculator. You've already got this plugged in to your graph. Now you could plug y equals 9 in and figure out where they intersect. So that could be one way. But, you know, since I love algebra so much, why not use a bunch of algebra? So I'm going to subtract 2 from both sides. Multiply by 3 over 2. And then use that definition of logarithms to rewrite this as an exponential. And then plug that into my calculator. And you get approximately 31.6 trillion tons. This goes with C. So true or false? Doubling the energy released by an earthquake doubles the Richter magnitude. Give evidence to support your answer. Okay, I'm going to do this pretty easily. I'm going to make a table of values. I really like a table of values. And I'm going to start with 1,000, which we started with. And then I'm going to double that each time. So if I double it, I'm going to get 2,000. Then doubling that, I get 4,000. Doubling that, I get 8,000. Going into my table setup, I'll start at 1,000. I'll increase by 1,000, but I'm going to want to make sure that I get my correct x values. So at 2,000, it's approximately 4.2. At 4,000, I can see it's approximately 4.4. At 8,000, it's approximately 4.6. So are the magnitudes doubling every time? And they're not. What I see instead, so I see over here that these are doubling each time, times 2, times 2, times 2. But what I see over here is that each time it appears that I'm adding 0.2. So this is an example then of a logarithmic function, because as we all know, well, first of all, we knew it was a logarithmic function, but then what we've also learned is that logarithmic functions have that multiply add pattern. I'm going to do a couple of examples out of the book with you. So this is on page 108. I'm going to do number 8 and number 10. Some graphing. So 8 is f of x equals log of, I think they put 3 minus 2x. Now for me, it's a little bit easier to put the x first so I can see what's happening. So I'm going to rewrite that. And now I can think of this as, you know, with all of those shifts and reflections and all those other things that are happening. So I know that by adding 3, I was really subtracting a negative 3. So I know that this graph is going to shift left 3. I know that by multiplying my input by 2, let's just look at the 2 first. This is basically going to be that horizontal dilation. By 1/2. And then by negating my inputs, so this negative here, it's not happening to the whole function, so it's not a reflection across the x-axis. This is going to be a reflection in the y-axis. Okay, so getting a ruler so I can make this somewhat neat. So my original graph would have been a logarithm that looks something like this. That's my parent graph. But now I'm going to shift it left 3. And with that, the asymptote also gets shifted. So that asymptote that used to be at the y-axis is now going back 3. 1, 2, 3. So now I've got this asymptote. Now this isn't all going to stay here, so I'm kind of writing lightly. But I find that it helps for me to really shift everything and see what's happening. So I'm going to shift that back now. This point, which I know is 1, 0, is going to get shifted back 3. 1, 2, 3. So it ends up at -2. Okay, so really now, and you don't have to draw this, but my graph is going to look something like this. However, I've got that horizontal dilation by 1/2. So really this point isn't at -2. This point is actually at -1. And where's my asymptote actually at now? My asymptote is over here. Oh, not even there. It's half of 3. So it's at -1.5. Okay, so it might help. And you might want to do this in a couple separate graphs. It's up to you, whatever it takes to help you remember these things. So now I know that my graph is looking like this. But then I've got this reflection. I need to reflect everything in the y-axis. Okay, so that means that my asymptote gets reflected over to +1.5. And this point gets reflected over to +1. So I've moved everything. So now the next thing we can do to get more points to make it more accurate, because I have a pretty good idea, it's going to look something like this, but to be more accurate, what I can do is I can turn this into an exponential function. So let's say that it's y equals log base 10 of -2x plus 3. Well, I can say this is 10 to the y power equals the input, which is -2x plus 3. Now subtract that 3 and divide by -2. If I do that, I get this equals x. Okay, and then what I can do is make an input-output chart. But what's going to end up happening is I'm going to plug in the y's and then get out the x's. So probably the easiest one is to plug in, 0. 10 to the 0 is 1 minus 3 divided by -2. So if I do that, I get -2 divided by -2 is 1. Okay, and you can put a bunch of these into your calculator and figure it out. But basically what you're going to find is that this thing is kind of stretched horizontally. So it might look something like that. It may even be flatter. And you can check it using your graphing calculator, right? Just go back up here and plug that in to your graphing calculator and check what the graph looks like. Okay, let's do 10. I'm going to flip over here. 10 is interesting. I don't think you've seen anything like this yet. So, oops, and I forgot the f of x part. So this is really interesting. You really need to think about the domain. Right? What are those possible inputs? So remember, you have that when you graph this, right? When you graph the parent graph, you've got this asymptote on the y-axis. So you end up with this graph that basically stays all x's being positive. All inputs have to be positive. Oops. So what ends up happening is all of your inputs here have to be positive. So whatever I plug in here has to equal 4 or greater. If it equals anything less than 4, I'm going to have a negative. So what are some numbers that I can plug in, and what are some numbers I can't plug in? Well, if I plug 2 in and I square that, that gives me 4. Now what you want to think about is 4 minus 4, well, that's going to be 0, right? So ln of 0, let's think about what that is. Remember, you don't put 0 in, right? 0 is not an input. It's undefined there because the y-axis is your asymptote. So in reality, we need numbers that are anything bigger than 2. So x needs to be greater than 2. Now let's think about that on the other side. Are there any negative numbers I could plug in here? If I plug negative 2 in and I square it, I'm going to get 4. 4 minus 4 is 0. Okay, so again, I can't plug 0 in, but could I plug anything less than negative 2 in? Like let's say negative 3. Plug in negative 3, square that, that's 9 minus 4. I'm going to end up with 5. I can take the ln of 5. Can I plug in anything bigger than negative 2? So if I plug in like negative 1, negative 1 squared is 1. 1 minus 4 is negative 3. Can't take the ln of a negative. Okay, so I know that I'm also going to have any x values that are less than negative 2. Okay, now the graph of this is a little bit crazy. But basically what we have here is we have asymptotes at x equals 2 and x equals negative 2. And then what we have is we have this logarithmic graph that basically goes just like a regular logarithmic graph, but then it gets reflected on the other side. Now, I'm not going to go through and find specific points. You could do it just like we did number 8. But overall, the graph looks pretty much, gets pretty close here, something like this. Well, it's a reflection. Pretend like that's a reflection. It's not exact. If I were you, I'd go into your graphing calculator and I'd get some actual points using the same method that we did by turning it into an exponential like we did on number 8.